All right, let's choose a problem here. All right, let's do number. All right, let's do number 14 here. Practice problems. I'll zoom it up for you. And then do the autofocus. Get this thing out of the way. All right. 3 identical balls are released from the same height. Ball A is released from rest. Balls B and C have initial velocities in the direction shown. Which ball, or more than one, reach the ground first? Okay. A is B and C reach the ground first, together first. B reaches the ground first for B. For C, A reaches the ground first. D says C reaches the ground first. E says A and C reach the ground first together. Okay? I'll open this up. Oops, I didn't do that. Okay. All right. I think this is not a problem that takes a lot of time to work through, so go ahead and make your choice. And let's see what people have said. Everybody made a choice? Okay. So, a lot of people say E. All right. Now let's take a look at the solution. So this, again, comes from a practice test from another course I taught years past. So I'm taking these clicker questions from this test, but I'm posting the whole practice test on your D2L webpage. So all the other problems are there for you to practice up during this practice folder. All right, so let's just take a look. Solution. So the x motion really doesn't matter because the ground is flat. The x motion doesn't determine when it will hit the ground. Okay. So A and C will be equivalent to each other. Then it's just a matter of figuring out whether B is going to hit the ground later or before. And clearly, because B starts up, it takes time for it to turn around first. And it doesn't somehow catch up to A and C. That's not how it works. If it's behind, it will stay behind. Everybody good on that? If you're not clear, sometimes when you do these conceptual problems, you may be not sure whether B might somehow catch up and go faster than hit the ground faster than it. All you have to do is just punch in some numbers. Let's say the velocity was +1 in the y direction. Just figure out what the time is, and then compare it to what you would get if the velocity in the y direction was 0. Okay. So what I'm saying is, if you're not certain on conceptual things, you can just do a simple example and work it out. Okay, any questions about that? All right, so then let's go ahead to the new material. Let's zoom this back out. All right, we are going to start talking about solving problems with Newton's second law. Okay. So let me consider a problem where I have maybe something like this, where I have a mass attached to a string. Okay. But let's make it maybe a bit more complicated. So you're going to face, not on this quiz, but eventually we're going to build up to problems that are somewhat complicated because life is complicated and you're going to learn how to solve things that are actually useful, not trivial things. So in solving problems, we will apply Newton's second law. Remember what that is, that F net is equal to the mass of the object times the acceleration. You can remember the net force is the sum of all the forces on an object. And we'll apply this to individual objects as well as combinations or groups of objects. Okay, for example, suppose we had some sort of a problem. Let's suppose I have two blocks here, and they have masses, let's say M1 and M2. Okay, M will be the generic symbol we use for mass. Let's suppose they're just in outer space, but let's do something interesting, and let's tie a string between them. So the straight line is just supposed to be a string, and let's say there's another string on this side. And you might be interested in understanding what happens to these masses if I start pulling on the right end string. Okay. We're not going to actually do this problem right now. We're not quite equipped to do it. But in this example, we might analyze what happens to mass number 1. So we could take this guy. I'm just going to put a little dotted box around it. So we're focusing on M1. So what we would do is we would say, what are the forces acting on M1? Okay. So let's just imagine we're in outer space, so we don't have to worry about gravity for this little example. And the only force that will be acting on this mass M1, okay, so let me put the box around it again so you can see, would be some force coming from this string that's attached to M1. All right, does everybody agree with that? That's the only force that's acting on that thing. Okay, and it's going in that direction. So I would say, let's say M1 has some acceleration. Let's say it's going in this direction. It better be going in that direction because that's the way the net force is going. So that's some acceleration vector, A. Okay, and so we would say, so this is acceleration of M1. And the formula we have is that F1, which is, because there's only one force, the net force is just that force, F1 is equal to M1 times A. Is everybody comfortable with that? It's just like what we did here with the demo. We said, here it came a little bit late. You see that? We have, so we just have the string pulling in this direction, and so, right, we have acceleration in that direction, and F1 is equal to M1 times A. Any questions? All right. Now, so that would be if I was analyzing M1, but we can also do something a little bit more clever or complicated, whatever you want to consider. We could also consider M1 and M2 together as an object. Okay, and consider both together. You can use Newton's second law this way as well. And so let me separate these out so you don't get these two things confused. So we can consider what are the forces acting on the M1 plus M2 system. Right? And for this case, I would not consider this little string connecting M1 and M2, right? Because that is just the internal structure of M1 and M2 as a system, right? One thing I can mention, like for example, my body has different parts to it, and you could say there is forces that my muscle next my upper arm to my lower and upper arm, okay? But that would not be a force acting on me. That's internal to me. Does that make sense? Right. So when you do Newton's second law, we're talking about what are called external forces, things that pull or push on the whole system. So this guy is going to do something on this system, whereas this one really doesn't do anything because it's part of the system. And the reason why it doesn't do anything is it actually pulls on both sides of the system in a way that cancel out. In other words, there's a force going this way, and there's a force going this way, but when you add them together, they cancel out, so there was no point in considering it to begin with. Any questions? Is everybody good? So we're looking at just the external forces, things that are external to the system. And so let's say there's a force F2 like this, and let's say there's an acceleration of this system, and the acceleration is some vector A. Okay. And it's going to also go in this direction because we know the way Newton's second law will work. Okay. And so in this case, we would say that F2, the sum of all the forces on this guy, M1 plus M2, is equal to, now what mass would I use for this case? What mass do you think I should consider for Newton's second law? Both? Both make sense? Okay? Because we're considering it as a unit, it's the whole mass. So it will be M1 plus M2. And then the acceleration, we're calling that A. So the formula that we get from Newton's second law is F2 is equal to M1 plus M2 in parentheses times A. Any questions? Everybody's with me so far? Not so bad. So in the first case, we considered M1, and we said what forces are acting on M1? And that would be just the force of the string. And we're going to talk about tension in a moment. I'll go through tension, strings and tensions and stuff later in the lecture. But then if I talk, so then I have F1 is equal to M1 times A from Newton's second law, because that's the mass M1, has an acceleration A, okay, and then, so F1 is equal to M1 times A. Now if I have M1 and M2 together as a system, and then the external force that's pulling on it is what I'm calling F2, then F2 would be equal to M1 plus M2, because that's the total mass of the system, times its acceleration A. Okay. Questions about this? These diagrams I'm drawing are what are called free body diagrams. These are examples. These are examples of free body diagrams. Or, yeah, free body diagrams. These are sketches. Where only one body, or a group of things considered as one body, where one body is drawn and all forces acting upon it. Okay, and so I'll just say explicitly the body might be a group of several objects together. That's fine. Okay? All right, so an example, prototype example, maybe with more than one force now acting on an object. Suppose I have an object that has some weird shape like this, and it has a mass m. And let's suppose there are two forces acting on it. We have a force going up like this, F1, okay? And then let's say there's another force like this F2. And then you would say the sum of the forces F net. Okay. That will be the sum of F1 plus F2. And this F net is also equal to the mass times the acceleration. Okay. So when you do Newton's second law, it's a two-step thing. First you get the net force, so we write down the expression for the net force, and then it equals the mass times the acceleration of the object. Let me hide this here. Everybody follow me? This is not so hard. It's good. Okay, now we're going to talk about gravity. So gravity is this probably the simplest force that we're going to deal with. So force of gravity. Your book already starts talking about the universal law of gravity and how everything attracts each other. But we're not going to be using that really in the problems for this part of the course. So I'm not going to go into that full detail. If you want to see that, your book has this formula. Capital G times M1 times M2 divided by R squared. Okay? And what that is that any two objects with mass actually attract each other. Except it only is really something you can measure when one or both of the objects are really massive. So for example, take a look at the person sitting next to you. You are actually pulling on him or her with an attractive gravitational force. You really are. And if you could measure it, you could determine your masses and your separation distance. Okay? But it's on the order of something like, if you calculate it, it's like 10 to the minus maybe 10 to the minus 8 newtons or something that you're pulling on each other. So it's pretty small. But the force you do feel is the attraction you have between you and Earth. And the force points towards the center of the Earth. Because the Earth is pretty close to the sphere, the way that the force points is as though all the mass of the Earth was contained at its center, at the center of the Earth. So gravity will be pointing to good approximation to the center of the Earth. Okay? And in this course, you can just think of it, the Earth is the sphere. But we're going to be talking about gravity on the surface of the Earth. And because the Earth is so large, thousands of miles in diameter, in this room, you're not going to really be able to determine, you're not going to be able to see much curvature in the surface of the Earth. So, because gravity points to the center of the Earth, it doesn't matter whether I'm here or over there, it pretty much looks like it's going straight down. Okay? It's because this room is so small compared to how much the Earth curves. It just looks like it points straight down to the center of the Earth. And so, the other thing is that the distance from, so the gravity actually here versus down there is a little bit different because the distance from this point to the center of the Earth and this point to the center of the Earth is a little bit different. But because the radius of the Earth is so huge, as I said, thousands of miles for the radius, a little bit diameter, you could ignore that difference and just say that the force of gravity points straight down and it has some, there's an acceleration associated with that that's going to be the same everywhere. Okay. Everybody good at this? Okay. So let me tell you the force of gravity on the surface of the Earth. Okay. So we're going to talk about on the surface of Earth. Okay. So let Fg be the force due to gravity. I think your textbook uses a capital G, but I find it a little bit easier to write with a small g because we use a small g for the 9.8 class. It reminds me of that. So for a freely falling object. Okay, let me stop and say, what is a freely falling object? A freely falling object is exactly what you think it is. It's an object that's freely falling. You let it go and it free falls. Okay? As it's falling down, there's going to be a force on the object due to gravity. For a freely falling object, the acceleration has magnitude g equals 9.80 meters per second squared. On the quiz, the formula sheet will actually say 9.81, but 9.80, it's off by 0.1%, so it's not a big deal. Okay, and it points downward. Okay, so this you already know about the acceleration. So, for a freely falling object, the only force on the object as it falls down, as it's falling down, the only force on the object is the force of gravity. Okay? Now, since that's the only force, from Newton's second law, we know that Fg is equal to, well, sorry, let me first say, because there's only one force, only gravity is acting. From Newton's second law, we can say that Fg must equal m times a, but we said that a has a certain value, okay? Right, so remember, this is the force of gravity, this is the mass, this is the acceleration. So the magnitude of the force of gravity is going to be m times the magnitude of the acceleration, which is small g. So that's m times small g, which is 9.8 meters per second squared. All right. Any questions about this? So the logic is, if something's freely falling, there's only force of gravity pointing down. You already know, we said from this course, that the acceleration due to gravity on the surface of Earth is 9.8 meters per second squared down. And so, using Newton's second law, F net is equal to m times a. A is 9.8 going down. So therefore, the force of gravity will be m times 9.8 meters per second squared going down, or m times g. Okay, any questions about that? All right, so this object, Fg, so if I just write Fg, that will just mean the magnitude of the force of gravity. And this is called, guess what it's called? A word that starts with W. Yeah, it's weight, okay? So this is called the weight of an object. Okay, sometimes you'll see another symbol used. Your textbook prefers small w, but capital W is also used for weight more often. And because it's a force, it has units of newtons. Okay, all forces have units of newtons. Now, I should mention, if we weren't on Earth, but we were on, let's say, the moon. Okay, if we were on the moon, then the force of gravity, or the weight, force of gravity, would be, let me write W here this time. W, the weight, would be equal to m times g something else. So let me write it as g prime. And so this g prime, that will be the gravitational acceleration on the moon. Okay, so it's just a simple formula, if you know the gravitational acceleration on the surface of whatever, a planet or a moon or something else. I was going to say star, but it's unlikely you'd be standing on a star. That's kind of then the force of gravity would be m times that gravitational acceleration. Okay, any questions about this? The next thing I'll talk about is tension due to a string or a rope. Tension. All right. Now, so what we're talking about with tension is this. So we have a string. Okay, the first thing you notice about a string is that it exerts a force. I can pull my one hand with the other with the string, okay? But the other thing you should know with the string is I can't push with the string. It doesn't really work, okay? There's no pushing, it's always pulling. So the string, the property of a string or a rope is that it always pulls inwards. Okay? The tension, capital T, is the force that a rope or a string exerts as a pull on each end. Okay, so when I write T, I mean the symbol for the force, but without the direction, because the direction will be indicated by arrows. So let me show you like this. Suppose I have a mass here, I have a mass here. Maybe there's another string pulling on this side, but I'm going to focus on the string between the two masses, and there will be some tension in this string. So imagine having these two masses, and I pull on this, then there will be some tension in between the two masses in that string. And what it will do is it will pull like this. It will pull on the mass m1 to the right with force capital T pointing to the right, and it will pull to the left with the magnitude capital T on mass number 2. Okay? So note the magnitudes of forces on the ends are the same. Okay? Any questions about this? Very good. So now let's try a more complicated problem. We'll do it together though. Let's see. I'll start it here. Okay. Let's say a 7.5 kilogram bucket is lowered by a rope with tensions 63.0 newtons. The question is, what is the acceleration of the bucket? Okay. And we can ask, is it accelerating upwards or downwards? Okay. All right, this is a little bit complicated, but let's first do the first step, which is do the free body diagram. We draw the free body diagram. Oops. Okay, so I have a little bucket. I'll just draw this little cylinder. and I will have forces on this bucket. So somebody tell me, what's one force that's on the bucket, acting on the bucket? Gravity. Which way does it point? Down. Okay, so we'll have force of gravity, Fg, and so this is gravity. Okay? And what's another force? Yeah, tension of the string, or the rope, whatever it is. I said a rope, so I have some tension. So I don't really know which one is bigger. Let's just call it T, that's the tension. Now I have, let's take positive y to be in the up direction like this. Okay? I always like to go with it pointing up. So now what we're going to do, notice, pay attention to the fact that I don't put vector hats on these symbols right now. Fg is just the magnitude of the gravitational force, the gravity force. Okay? There's no direction implied. The direction is actually encoded in the fact that I've drawn an arrow here. Is everybody okay with that? I'm not putting a minus sign in on it. It's just going down because the arrow is pointing down. T is the magnitude of the tension. So if I do it that way, then when I write down an equation for the force, the net force in the plus y direction, or in the y direction, well, I don't need to say plus y, that's kind of funny. In the y direction, then I would say, okay, let's get the net force in the y direction. So T is pointing in the positive y direction. So I'm going to write down positive T. So everybody is good with that? This T is the magnitude, so it's pointing up, so the component will be positive T, or plus T. But Fg is pointing down, so is everybody good on saying it's minus Fg? Does that make sense? Because Fg is the magnitude. Because it's pointing down, I need the minus sign to get the actual complement. All right. So now we can write down that the tension, okay, tension we are told is 63 newtons. All right. We don't know well, okay, so we do know, but I just didn't write. Let me just do it in 2 steps. So how about m times g? Okay, so let's do that side. Okay, Fg is m times g, so I make that replacement. Then the bucket is 7.5 kilograms, and then g is 9.8 meters per second squared. All right. Everybody's following me on that? And you can multiply these two together. You take the difference, and this minus this one, and you get minus 10.5 newtons. Right? Now, if I'm going to try to figure out which way the acceleration is going, the next part of the Newton's second law is F net is equal to m times ay, the y component of the acceleration, ay. So everybody is with me on this? Okay, Newton's second law, first you get the net force. You add the forces together, and then you say the net force is equal to m times the acceleration. So we're just focusing on the y component here. Okay, so then I can get that ay, because that's what I want to know. It's going to be F net, y component divided by m. So then I will have, we figure this is the net force y component. Divide by the mass, we get 7.5 kilograms. All right, and that comes out to minus 1.4 meters per second squared. So which way is the bucket going? Is it going accelerating down or up? Yeah, down, because the y component is negative, so it accelerates down. So it's down. Okay. Any questions about this? All right. The next thing we'll do is do another quicker question to review for the quiz. Let's try to decide on something. That would be good. Okay, let's take a look at number 11. Oops, where is that? Focus. Come on, I've been stop focusing. Oh, there it goes. Okay, if the ball, oh, sorry, this is 2 parts. I gotta, all right, okay, so we gotta do part, do we have enough time? Let's do the first part then. Okay, let's start with the first part. If we have time, we'll do the second part as well. So, a person throws a ball straight up into the air and then catches it. While answering the questions, assume that up is the positive y direction and air resistance is negligible. Okay? And the first question is, which velocity versus time plot below best represents the velocity of the ball as it goes up and comes back down? Okay? So it's a bit of a review. Let me zoom out so you can see both of these things. All right, let's do that. By the way, last week we talked about angles, we talked angular motion, we talked about angular velocity, angular acceleration. Right? So this problem, we talked about velocity versus time, but you could also imagine these were plots of angular velocity versus time. So everything we learned about for velocity and acceleration, it applies just the same for angular velocity and angular acceleration. We'll do problems later on that. Okay, so this is a bit of a review. So go ahead and make your choice. Hopefully this is relatively straightforward. So it starts going up, and then the question, what's the plot of velocity versus time, the y component? Okay, if you haven't already made a choice, go ahead and make your choice. Okay, let's see what people said. All right, a lot of people say E, a few people say C. Okay, the plot, right? So it starts off in the positive y direction. It has to start off with a positive value, but we know that there's acceleration going down. So the velocity will just have a straight line plot with a slope down, because the slope of the velocity versus time is the acceleration. Acceleration is negative 9.8 meters per second squared, so it has to start from positive value and have a straight slope down. Okay? Okay, now let's do number 11. Okay, if the ball reaches a maximum height above the person's hand of 7.1 meters, how long will it take to reach that maximum height? Let's go ahead and do that. there's several ways to do this problem. You might be annoyed by the fact that you don't know the initial velocity, right? Yeah, that might be bugging you. You can either do the problem in 2 steps to figure out what the velocity is. You might be able to figure that out. And then use that to figure out the time. So that's one way. Or if you want to be clever and lazy, we go together, you know? A lot of cleverness in human history is about being as lazy as possible. You can actually think about doing the process in reverse. So in other words, instead of the ball starting here with some velocity going up to the top, you can think about, suppose the ball was already at the top and going backwards in time, how long it would take to get to the top. Okay, so try that. Okay. By the way, so this trick about reversing the direction, it's kind of helpful for these projectile problems when you throw something, right? The time it takes to get to the top is the same time as it goes from the top to the bottom. It just goes back at the same time. So sometimes that will make will give you a shortcut. All right, go ahead and make your choice. All right, I'll close it up and see what people have said, and we'll quit for today. So after we go over the solution, so a lot of people say B. All right, so let's go over this. Let's do the shortcut since we're running out of time. You can do the 2-step solution if you like, but you can say we do the reverse process. The initial velocity is 0. It starts from the top, and it's going to fall down. So you just simply have 1/2 AY delta t squared. Okay, and because the initial velocity is 0, that's going to go away, and that's equal to y minus y0. Okay, and then the acceleration in the y direction is minus 9.8. You have delta t squared. Y minus y0, that drops negative 7.1 meters. Let's not use the units. And we multiply by 2, because 14.2 divided by 9.8. Minus signs go away, and we get 1.2 seconds. When we take this, we have to take the square root as well. We get 1.44, take the square root of 1.2. All right, I'll see you guys on Wednesday.